your gates, you're concerned with power, you need to understand capacitance. Okay, it's a very, very important important part of the VLSI circuits. Okay, power depends highly on capacitance, dynamic power, and delay. The speed of your gate also highly depends on the capacitance, so you need to understand really well the concept of capacitance in MOS transistors. Okay, so what it means by capacitance here, when we say capacitance, is basically, you can think of it sort of like an imaginary capacitance. It's not the real capacitance that we put intentionally. Okay, it's by design, or you can say by accident, CL appears because of the so if you remember in the earlier slides, we have the cross section of the MOS transistor, and in the cross section you can see there's metal there, right? So remember, if there's two metal plates coming together with a dielectric in the middle, then you are basically creating a capacitor. Okay, so basically in MOS transistors you have a lot of metal plates. They are joined together, and all these metal plates or all these capacitors can be all lumped together into one called the load capacitor CL. So in here we are interested to know what are the components of CL. Okay, so for example here we have inverters. So you can see the transistor the transistor level design of two transistors, back-to-back transistors, and we have a CL in the middle. So we are interested to know what is the CL on the output node. Okay, on the output node. So here is the output node. Okay, here is the output node. So what is the load capacitance of the output node? Why we are interested in that is because at the end of the day we are going to charge or discharge the node. Okay, so if you want to have a logic 1, you're going to charge node out, and if you want logic 0, you're going to discharge node out, and the charging and discharging occurs on the load capacitor. Okay, so we need to know what are the components of CL, right? So in here basically you can divide into three parts. So we have the first component is the intrinsic MOS transistor capacitance C dB1, dB2, and GD12. All right, so dB1 is drain to bulk. So you have so if you see here, this is a drain. Okay, this is the source. Okay, and here is the bulk. Okay, here is the bulk. Okay, so here is drain 2, bulk 2, source 2, source 1, bulk 1, drain 1. Therefore you can see actually the bulk is connected to our drain, and we have a capacitor C dB1, C dB2. Okay, and those are called the intrinsic MOS capacitance. And then we also have CGD12, gate to drain. So gate to drain, we have the gate of the, okay, here is your gate 2, gate 1. So we have a capacitor, or you can say two metal plates, a gate which is in polysilicon, connected to the drain which is normally in aluminium metal. Okay, so two metals connecting together is a gate to drain and is impacting our output node. Okay, and then we also have the intrinsic MOS transistor capacitance. So the intrinsic is actually the output, the input to the next stage, basically. Okay, so the input to the next stage. So CG4 is the capacitor from the gate of the second the gate of the second device, the gate of the second logic gate, okay, of the inverter. And CG3 is the gate of the NMOS. Okay, so here, gate of the NMOS, gate of the PMOS. Okay, and then you also have CW. So CW, you have the capacitance on the wire itself. Okay, so wire also contributes to a capacitance value. Okay, the longer the wire, the higher the capacitance. Okay, Okay, so all this, if you plus them all together, we get CL. Okay. So what are the components in the capacitance? So basically you have an overlap capacitance, you have channel capacitance, and you have the depletion region of the reverse bias PN junction of the drain and source. So let's have a look. Okay, so looking at this, so you have to imagine a little bit that let's imagine this is actually, okay, so it's an NMOS. Okay, so imagine NMOS, and remember that two metal plates together with the dielectric in the middle creates a capacitor. Okay, so the first thing you want to see here is the overlap capacitance. Okay, so what is the overlap we are talking about? So we are talking about the overlap between the, okay, so this is the source and this is a drain, and if you can see here, there is a overlap between the source diffusion and the gate, and then you also have an overlap between the gate and the drain diffusion. Okay, so where is the capacitor? So basically you have a metal plate here on the drain, on the gate, and then you have a metal plate there, okay, on the source, and here also some metal plate. So you are creating an overlap capacitance, okay, between the gate and the diffusion layer. All right, so how do we model that? So to model that, basically this is the capacitance. If you want to see, it's actually here. Okay, the capacitance is there on the, if you measure from the top, and this is called the capacitance gate to source overlap. Okay, and here is capacitance gate to drain overlap, and it's given by this equation here. Okay, so what this equation is saying is basically Cox here. Cox is actually oxide capacitance, oxide cap per area. Okay, gate oxide cap per area. So basically we have the capacitance there per area, and if we multiply with the total area of the capacitor, then we get the overlap capacitance. Okay, and this can be simplified by CO, and now CO is the gate oxide cap per length. Okay, per length, and you just multiply with W, you get the total, the actual value of the capacitor. Okay. Okay, so next, the gate to channel capacitance depends upon the operating region and the terminal voltages. Okay, so now we already have the overlap here. Okay, we done already, and here, okay, you already know how to get it and how to analyze it. But what about the capacitance here? Okay, you can see this area here, and this part here. Okay, this capacitor here is called the C gate to channel. Okay. So C gate to channel, which is the non-overlap part. Okay, the non-overlap part with the gate. The non-overlap in the channel with the gate. Okay. So CGC depends on operating region. Okay, so the capacitance in the middle there actually depends on what region. Are you in the cutoff? Are you in the linear region? Are you in the saturation region? Different region will give you different capacitance. Okay, so what is where we are doing here is CGS, gate to source. So gate to source actually is trying to divide into two. So gate to source is here. You can see. C gate to source, and this part here is C gate to drain. Okay, so C gate to source is the overlap plus the channel capacitance. Okay, C gate to drain is the drain overlap plus the channel capacitance. So let's see what is the actual value of the capacitance based on the region. Oh, another thing is the CGB. CGB is basically the gate to the bulk. Okay, the gate to the bulk. So you have the bulk here and the gate you also have a capacitance there. Okay, so we're going to look at what is the component of CGC. What is this actually in the middle? I think it should be the next one. Okay, so the interesting part here is actually we want to look at the total gate to channel. Okay, the total gate to channel, and here is a total gate. Okay, total gate means including the overlap. Gate to channel without the overlap. Okay, so gate to channel, remember, gate to channel is actually gate to channel source plus gate to channel drain. Okay, but in the cutoff region it's a little bit different. Okay, so in the cutoff region you don't have any gate to channel source, gate to channel drain. The capacitance is directly gate to bulk. Okay, because it's not on. There's no electrons moving. There is no basically you can say the array is not metal. The metal now is actually the bulk. Okay, so you have the full Cout WL effective. Okay, which is not including the overlap, because remember the overlap is constant. Okay, it doesn't the overlap capacitance GSO GDO does not depend on the operating region. It's a fixed value, so we're only looking at the gate to channel without overlap. And in the cutoff region, okay, so in the cutoff region is just the full Cout WLF, and the total gate therefore is Cout WLF plus the overlap. So this one here is the overlap component, which is constant. Okay, now let's look at the linear region. So in the linear region, now you have current flow. Okay, you have current flow in the channel, and therefore your gate to bulk now is 0. Gate to channel source, on the source side is half. Okay, half of the capacitance, and on the drain side is also half. So half goes to the source and half goes to the drain, and the total is the same, Cout WLF, and the total gate including the two overlap is this one plus this. Okay, let's look at the saturation. Again, you have current flow inside during the saturation mode, and therefore your gate to bulk is 0. And now remember we have the pinch off condition. So because of the pinch off condition, now you have more capacitance on the source side. Okay, because you have the pinch off on the source side. So because of that, then you have actually can be calculated to 2/3 of the whole capacitance without the overlap, and the gate to channel for the drain can be estimated to 0. Okay, it's not exactly 0, but you can for now we can estimate to be ideally 0. Okay, so the total on the channel is 2/3, not full anymore, and then including overlap just plus 2 COW. Okay, so channel capacitance components are actually non-linear and they vary with the operating voltage. Most important regions are cutoff and saturation, since that's where the device spends most of its time, where we have current flow. Okay. Okay, so the junction capacitance is from the reverse bias source body and drain body PN junctions. So now we're looking at the diffusion capacitance. So what is diffusion? So diffusion is essentially this part. Okay, so here we say it's a diffusion area, and here is also diffusion area. Now, what is the capacitance on the diffusion? Now we already look at the capacitance based on the gate. Okay, so we have capacitance on the gate, and we also have capacitance on the diffusion source, diffusion drain. And how to calculate your capacitance on the diffusion side? Okay, so source to bulk is simply the source diffusion, and drain to bulk is the drain diffusion. And yeah, basically first we are looking here, okay, the source to bulk and the drain to bulk, that's one. And then you also want to find out what is your diffusion the total diffusion is basically the capacitance of the bottom plate. Okay, so here is the bottom plate, and then the sidewall. Okay, so the capacitance, what is the capacitance here? This is the bottom plate capacitance plus the capacitance on the sidewall plus this one plus this one. So there's basically 4 components. Okay, the bottom plate, 2 sidewall, and 2 sidewall on the side. Here it doesn't count, okay, because the signal doesn't go through there. I mean, we have the current flow, okay, but it's not writing. It's not using the capacitor there, okay. So basically it's going to count only here. If you see here, 2Ls plus W. But let's look at this one. What is CJ area? What is CJSW parameter? So CJ area is basically, CJ here is so the bottom plate capacitance per unit area, okay, bottom plate capacitance per unit area, and CJSW is the sidewall capacitance per length. And what is the total length? The total length is this one, capacitance per length of the sidewall. And here is the area of the bottom plate. LSW is the area of the bottom plate, and CJ is the total capacitance of the bottom plate per area. Okay. Okay, so for this one, I'm going to skip this one. This one is not it's not so useful for now. You can read through yourself regarding the reverse bias diode and how to simplify further the capacitance equation. But we're just going to use the original one. Okay, so the one that we just discussed. And finally, we arrive to our MOS capacitance model. Okay, so what is the component in the MOS capacitance? So we have the gate to source. Okay, gate to source capacitance. So imagine it's a half of the capacitance from the gate to the source. Gate to drain is the other half from the gate to the drain, and it consists of the channel and the overlap. Okay, and also the drain, channel, and overlap. And here we can also look at the source to the bulk. Okay, the source diffusion, which is basically what we just discussed just now. It consists of the bottom plate and the 3 sidewalls. Okay, the drain to bulk also consists of the bottom plate and the 3 sidewalls, and then you also have the gate to bulk capacitance, which occurs only during the cutoff region. Okay, so let's quickly go through the example here. So in order to understand better the MOS capacitance, so we have an NMOS with L effective 0.24, W 0.36, and then LDLS. If I did my calculation correctly, this is the correct value. Okay, so not this one. Okay, so let's see. Let's see here. So if you can imagine, basically what happened is you have the gate, okay, and then you have the diffusion area and plus, and then and here is your L effective. Okay, your L effective there, and then you have the overlap region. So here is your overlap. It doesn't give you the overlap region, but then it also gives you your W, and then it gives you LD and LS. Okay, and remember, LD and LS is basically your area of your diffusion area, right? I mean the length of your diffusion area. So this is, let's say this is source and drain, so this LS, D, something like this. Okay. So where's the capacitance gate to source overlap? Okay, gate, remember, so gate to source overlap, we are looking at this area, this small region there, gate to drain overlap, assuming the overlap length is the same. So basically it's a COW. Okay, the capacitance per length times the total length, times the width. Okay, so how do we get CO? So CO is coming from here. CO is coming from here. So it's 0.31 times W 0.36, and you get this. Okay. Okay, so what is your total gate to channel? So gate to channel, assuming this is in cutoff, okay, in cutoff. Let's say it's cutoff. Okay, so in cutoff, your gate to channel is here. So we are looking what is the capacitance there. So the capacitance there is simply the gate outside capacitance per area times W times the L effective. Okay, so here we can see it's 6 times W.36 times L effective 0.24, and you should be able to get this. Okay, and what is the total gate capacitance? The total gate capacitance is the two overlaps plus the channel. So this is your CGC, this is your CGSO plus C GDO. Okay, GSO GDO, C gate to channel. Okay, and we should be able to get this. And then finally we want to check what is the diffusion. Okay, this side, this part here, the diffusion capacitance. So we have the bottom plate. So the bottom plate, okay, so the bottom plate is simply CJ0. CJ0 is 2 LSW. So remember, CJ0 is simply the capacitance of the bottom plate per area. So CJ0 is 2 times LS 0.625 times 0.36. You should be able to get this. And the sidewall. So the sidewall is looking at CJSW 0. This guy, okay, 0.28 times this thing, 0.625 times 2 plus 0.36. Okay, and you should be able to get this. And that is your sidewall capacitance. So the total diffusion capacitance, so we are talking about the total capacitance on the diffusion side is just this plus this, 0.9. Okay, so I think we are done with the MOS transistor chapter, and next we'll combine two of the MOS together, the PMOS and the NMOS together to create an inverter, and we're going to analyze the inverter in detail.